Hello, class. Today we're gonna cover an important class of problems called transportation problems. Transportation or logistics are important topics in supply chain, a great growing area in no matter what the organization is. And so it will be useful to know some of those models. They also are not just used in physical transport. They are used in other applications that you can't even imagine. They can be modeled as a transportation problem. And so they may be used in equipment replacement. When should we replace an equipment? Something nobody thought about until, again, a researcher discovered that it can be modeled as a transportation problem. Has nothing to do with equipment replacement, but it can be modeled as a transportation problem. So the transportation problem belongs to a bigger class of problems called network models. So when anytime you can model a problem, graph it, represent it graphically, then you can be able to apply these network models and model it that way. There is a huge benefit to modeling a problem as a network problem. And let me tell you why. Because when we covered integer programming, we said that will add certain restrictions, adds constraints, which makes the problem more time-consuming to solve and more difficult to solve. Well, there's a special features of a transportation problem that if it applies, then that means the solution is automatically going to be integer, and you do not have to add integer solutions. And so there is a lot of activity among researchers to try so much to model the problem as a network problem because they want to avoid those restrictions and waive those constraints. So the transportation problem, against the most basic with no extras, is you have a set of locations, the one that we can imagine very quickly. We have plants, we make a product in these plants, and then we have customer demands in regions for this product, whether it's cars, motorcycles, bikes, whatever it is. Each plant has a limited amount that it can ship, so there is a capacity or supply constraint. Each customer destination must receive a required quantity of the product, so there is demand constraints. Customers need a certain demand depending on the region. Each plant may have a different capacity to make the product. The unit shipping cost and the possible production cost come from a transportation cost analysis, and so the cost from each plant to each region can be just transportation, but more meaningful, and what companies use is they include the production cost as well. And the reason production costs makes a big difference in how you ship your product is because we know that a product may cost more to make in certain regions of the US or the world than other regions. And so, this could make a big difference in your optimal cost if you're trying to minimize total cost. So graphically, this looks like this. This example in your book has 3 plants where we make the product. And we have customers in 4 regions. These could be states, regions, all over the world. Doesn't have to be just the US. And so the plants can be anywhere, the regions can be anywhere, but next to the plants, we always have capacity or supply. So I should have put capacity up here or supply. We can make and supply 450 from plant 1 units, 600 from plant 2, 500 from plant 3. The region this is a demand next to the region, next to the customers. That's a demand for each region. And this is the cost to make and transport each unit from a plant to a region. And so that's, the cost per unit, of course. So this trick that I told you, we do not have to add integer constraints, that the number we ship is integer, is if the supply numbers and the demand numbers are both integers, okay? Which they are in this case. And so, great, I would save a lot of constraints doing that. What's my decision variables? You may guess. It's how many to ship, make and ship from each plant to each region. And so currently 3 times 4 is 12. And so if we have 12 possible routes, it's not going to be very cost effective to ship, make and ship on each route. It's going to be more costly. Now, how do I decide which of these to use and how much to send on each route? And so this is exactly the optimal model will help us decide how much on each route, which of the 12 routes we use and how much we send on each route. So you can see this could be workers, machines, workers. This could be so many different applications that falls under the network models. So let's look at the spreadsheet. The template, I forgot to change the template, so excuse me. Actually, no, it is the right one because you have all the problems in the same place. So the shell for this problem would look like this. I mean, unit shipping cost, shipping and production cost is this per unit. And the decision variables are going to be how much to ship, 12 decision variables, how much to ship from each plant to each region, and the demand and the supply, the capacity. And we want to minimize total production and shipping cost, or just total shipping cost. So this is the layout, and it's called a matrix layout because it's intuitive. You can see that it's intuitive to model it this way. So if we look at the solution to this, again, very simple model, only if you can guess it ahead of time, or you learn it somewhere, or somebody tells you about it. So the inputs are the cost figures, the capacity, the demand. Again, the very first thing you want to do actually is to check that there is enough capacity to meet the demand. Otherwise, we may get infeasible solutions. So that's something you need to quickly test from the inputs and sum the numbers. Okay, so we have total of 1,550 units capacity to make at the 3 plants. And we have demand for, let's see, what's the total demand? Total demand is, oh, great, 1,250. So we definitely have supply greater than demand. You don't want to have demand, total demand, much more than capacity, because then, it's going to come back, solver, and tell you this infeasible solution. I cannot meet your demands. It's okay to have more capacity than demand, because then you don't have to ship all the capacity of the plant. It'll be interesting, actually, to see which plants are not binding and have extra capacity. It will be useful information to management again. And so the decision variables are the 12 routes we have. And modeling this problem is a matter of adding. This is nothing but summing the columns, sum C13 to C15. What does the sum give me? It gives me how much demand was met, regardless of the plant, how much demand was met for region 1, because we want to make sure that that is greater than or equal to 450. And this is a formula that we just copy to the right because we want the same for region 2, same for 3, same for 4. You may already guess that the total shipped is also a sum of the row. How many did we ship out of plant 1, regardless of the region we shipped it to? Okay, it would be the addition of these cells. So it's a sum of the row, which we also copied down. Again, the beauty of having a nice layout that allows us to copy. So we want the total shipped from each plant not to exceed the capacity, so that's a less than or equal constraint, and the total received by a region to be at least 450. Now, since we have total demand less than total capacity in this problem, you can change these greater than or equal to equal signs, and it would work equally well. Now, coming to the total cost, we could multiply this times this plus this times this, 12 times 2, 24 times, plus another 12 operators. This is where our sum product formula will come in very handy. And so it would be sum product of this whole range, comma, this whole range. And so this is part of modeling that you need to learn. It's a very powerful a formula that probably your colleagues will be jealous of you for knowing, because it saves you so much time typing a very, very long formula. You don't need to do that in Excel. So that's all the modeling there is. You go to data and solver, and you see that setting solver is easy. The total cost is the objective function. We're trying to minimize it. The shipping plan, any guess? That's the pink cells. That's our decision variables, 12 of them, but I named ranges to make solver more readable. Total shipped is less than total capacity, and so that's total shipped. These 3 cells are less than these 3 cells, and total received is greater than demand. That's these cells are greater than or equal to this. Simplex LP, an integer programming is still a simplex LP, and non-negative constraints are always there. Notice there is no make these cells, the shipping plan, make all these 12 cells integers. Why? Again, because the capacity is integers, the demand is integers. Somebody proved along the way that that's enough to come up with integer solutions and save 12 constraints. So we click solve, and we say okay, and we have ourselves a shipping plan that meets the demand. Each region got its demand, and it didn't exceed the capacity. And so which constraints are binding? Plant 1 and plant 3. Plant 2 has 300 extra capacity. This is another way to use this model, not just to come up with production and shipping plan, but also if a business is going through some hard times and they want to downsize and close a plant, they use a lot of these models to decide on which plant to close. Similarly, if they're growing and business is doing good and there isn't enough capacity to meet the demand, where should we open a new plant? There's a lot of models on that too. But this is the most basic model, and it just gives us a shipping plan and the cheapest possible production and shipping cost, which is $176,000. You can be sitting here all day trying to guess these numbers, and you wouldn't get a better shipping plan than this. And that ends this video. We'll look at sensitivity analysis in another video.